upon where you are in the world, and welcome to today's Security Boulevard webinar. I'm Charlene O'Hanlon, moderator for today's event, and I welcome you. As always, we have a great webinar on tap today, but before we get started, we do have a few housekeeping items we need to go over. First of all, today's event is being recorded, so if you miss any or all of the event, you will have the opportunity to listen to it again later on. Following today's webinar, we'll be sending out an email that contains a link to access the webinar on demand. And we are taking questions from the audience. So if at any time during today's presentation you have a question for any of our panelists, please don't wait, don't hesitate. Just use your GoToWebinar control panel and submit your questions, and we'll do a Q&A near the end of today's webinar. And finally, we are going to be doing a gift card drawing. 3 lucky winners will receive a $50 Amazon gift card, and that drawing is going to be happening at the end of today's webinar. So stick around. Hopefully you'll be one of the 3 lucky winners. Okay, with that, we'll go ahead and kick off today's webinar, which is Don't Get Stuck in the Encryption Stone Age. Our speakers today are Steve Perkins, who is product strategy at Nubeva, and he is going to be joined by Eric Freeland, who is Director of Customer Engineering at Nubeva, and James Wenzel, who is an AWS Solutions Architect at Amazon Web Services. Welcome, gentlemen. Thanks for joining me today.
Hi,
Steve,
good morning.
Hi, Steve. I know you are going to be kicking us off, so I'm going to put myself on mute, let you get to it.
Okay, great. Well, thank you everybody for being here. I will kind of function as the MC through the content. As was mentioned, we have a Q&A at the end. Let me cover the agenda that we've kind of set out for today. Per the subject, this webinar is really about how to get decrypted visibility inside AWS. So to talk about that, we're going to first hit on some visibility foundations. We're going to move into a discussion around a new, very exciting feature set from AWS called VPC traffic mirroring. Then we'll talk about the decryption challenge on top of that and take a look at some solutions there and some use cases and end up with some Q&A. Hopefully this will be useful for everybody. So with that, let me get started into visibility foundation. So the idea of visibility in the context of this session today is really about helping organizations who need to inspect their traffic. And when we say inspect their traffic, we're very specifically talking about the ability to see their data in motion, not just in purely look at flow logs, and we'll cover that in a second, but actually to be able to monitor their data in motion, their application data, their API calls, the cloud and internet calls, their control traffic, whatever it might be, the need to actually monitor and inspect traffic. And why? Because that's where the action is. So this is a Security Boulevard session, so obviously with a security angle to this, the reason why you want to do that is to be able to look at multi-stage threats, encrypted malware, ransomware, SQL injection attacks. All these things happen inside the packets that require looking at actually packet payloads. It's also where bugs and misconfigurations lie and can be seen, as well as platform service traffic. So the idea here is that this is a function that's been done forever in private data centers. And as you move to the cloud, the business requirement doesn't go away. And in fact, AWS is very clear about, through its shared responsibility model, about the fact that customers are still responsible for their data. They're responsible for the security and the protection and the handling of that data, as well as the understanding of it. And therein lies the need to monitor and inspect your traffic to understand what's going on for security risks, for DevOps support, as well as ultimate lowering of risk and improving operations. Now, to do that, if we just start with some basics here, you really need 2 things. You need tools to look at the traffic with, and you need copies of the traffic in the first place. So looking at these from left to right, the good news is that today there are a myriad of tools available now in AWS and in public cloud. Most commercial tool sets are actually migrating their systems over either in hybrid mode or in native mode. There's also a large complement of open source tool sets that are actually becoming more and more mature and robust every day. So the fact of, hey, I used to monitor traffic and look at deep packet inspection or whatever it might be in my data center is now actually being solved in the cloud from the tool vendor or the tool and analytics side. But the traditional problem has actually been not that. It's been, how do I get my hands on the packets? In a data center, I can tap traffic. I got spans, I got mirrors, I got packet brokering infrastructures. Getting hands on packets is fairly commonplace. But in public cloud, when you don't own the infrastructure, that has traditionally been a problem. And it's there's been a number of fairly simplistic and cumbersome workarounds to date, but recently Amazon finally solved this part of the equation to unlock open-ended monitoring in the cloud with the introduction of VPC traffic mirroring. And so to talk about that, I'm going to flip this over to James, who can talk about VPC traffic mirroring and what it is. James?
Hi. Yeah, so let's get into traffic mirroring. I'm going to cover a overview of what can be done with traffic mirroring and how it works. It can be delved in a lot deeper and can be made a bit more complex, but for the purposes of this webinar, we're going to keep it down to the basics of what it's doing. So as you can see here, we have an animated slide that is showing an EC2 instance that's talking to the internet. Now, as was mentioned before, this would be difficult to find out what was going on within that conversation unless you had something sitting directly on that EC2 instance and sending that traffic back in one form or another, which would compete with its standard traffic or with the bandwidth it's using for production. So we've used traffic mirroring. The way that this is done is we basically mirror the traffic that is going on the EC2 instance, talking out the IGW to the internet by another instance called the monitoring instance. You turn on traffic mirroring. The traffic that goes out through the internet also gets mirrored over to the monitoring instance, allowing that instance to collect the packets. Even though it's collecting the packets, you still have to do something with it. So you can use any type of traffic analyzer that you want. You can use things that are baked into the operating system, if it was Linux or Zeek or something else that actually runs on the monitoring instance. But the packets are sent to you raw, just as the same as the packets are being sent out through the EC2 instance talking to the internet. And if you move to the next slide, you can see that there's a couple of reasons why we need to have this visibility. As was mentioned as well, in the traditional data center, this was always expected and known. There was two main pieces that people want to know. They want to know, am I secure? Are my packets going where they're supposed to be? And if I have a problem, can I look under the hood and see what's going on? Now, one of the things you can do with mirrored traffic is to see, hey, is my machine talking only where it's supposed to go? You could also see inside, as the payload of what I'm sending being sent, supposed to be going to where it's supposed to be sent. If I have a problem, can I look inside and see, hey, these packets are malformed, they have issues, they're getting dropped. All those scenarios can be wrapped in and looked at through traffic mirroring. If you go to the next slide, it could be argued that, hey, you have VPC flow logs. Now, VPC flow logs are a general overview of all of the traffic that's going on inside an entire VPC. That doesn't give you insight inside the packets. The other thing to keep in mind is that flow logs are not instantaneous. They're a batch process that's taken up over 5 minutes and then dumped either into CloudWatch or into S3. Traffic mirroring, on the other hand, is real. It's live at the moment. Traffic is going. You can also capture and see the packets at a given time. If you have a situation where you need to react because you see something that isn't going the way it's supposed to be, you don't have that 5-minute lag. You have the ability to see at that point in time something is going wrong and then react to that instance. That's pretty much how the difference between flow logs and traffic mirroring are. Now, there's some other things too, like flow logs. They use the standard source, destination, and capturing those pieces of information, what's in, where the packet was going. But within the traffic mirroring space, you can look inside and see what the payload is. That's the main difference. Batched, 5-minute delay, instantaneous, can look inside the packet. One shows you the traffic of the entire VPC. The other one shows you the traffic only for the instances that you want to mirror. Moving along. So there's the benefits of traffic mirroring the way we've done it is, first, it's native. We're not using any type of added on feature that you need to add to anything within your cloud other than clicking a button. So if you want to start mirroring, all you have to do is you have to name your target and your destination, and then you filter it out. You basically use native cloud constructs without altering anything on your operating system. The second piece is it allows you to capture your packets at the NIC level, right? So it's your ENI, your Elastic Network Interface. That is where you're capturing. So anything going in and out of that NIC, going in and out of that interface, you can grab. And then lastly, we are agnostic in terms of what you want to use for analyzing and monitoring those packets that come into your monitoring system, the target system that you're sending your packets to. We're not restricting you down to anything that is AWS only, specific vendor brand. The packets come in raw as it was leaving an operating system raw, whether it would be in the cloud or in the data center, it would look the same. And then it comes to you and you analyze it just like you would in any traditional data center. Moving on. So there are three main pieces. Two kind of add up to the third. We have targets, right? These are the destinations for the mirrored traffic. We have filters because we may not want to see absolutely everything or want to send everything into one location. And then we have the sessions. These are the things that are the actual operations that are actually doing the mirroring. Let's take a look at targets. So we have two different targets. When you are mirroring an ENI, you need to send that traffic to something. Those somethings that you can send traffic to are another ENI. Now remember, just for those who may be wondering, ENI, you've been saying this a lot. An Elastic Network Interface is a NIC that is existing in the cloud space on your instance. You can create new Elastic interfaces, and those can be moved. The other thing that you can send traffic to is a network load balancer. And this can be done for a myriad of reasons for horizontal scaling, depending on how aggressive you need to get and how much traffic you're sending through your networking space. Let's take a look further on. So a traffic mirror target can be used in more than one traffic session. There are many reasons why you'd want to do this. You may be wanting to segment the type of traffic that you're trying to see, but the destination of each of those segments, which goes into our next topic if we move forward into filtering, into filters, can help segregate this. So when you look at a traditional packet, there's a lot of information here that you can grab. Those things that are within your source, your destination, your payload, one small communication can be a lot more than what you're really looking for. And that doesn't really help you in any type of troubleshooting or security posturing because you still have to go through a lot of the noise. So we introduce packet filtering. So let's take this packet, for example. There's too much information that we don't want to see. So to filter that down, we want to go down to just what's coming in. We want to know just the TCP protocol alone. We're going to say it could be from anywhere on the internet, any port. We want to go to a particular machine, and we want to go onto that particular machine's port 80, and we want to make sure there's no truncation. That way we can see general web traffic as opposed to any type of ARPing, any type of other communications with, say, databases. We want to filter all that away so we can look at what we need to analyze at that point in time. Let's move on. So let's continue forward to session. So when you look at a session, these are the abilities to set up the mirroring and the targets and have each one of those have an individual ID. And you can set up multiples, as we mentioned, a maximum of 3, and you can set up the priority of each of those IDs. So you can have high priority traffic, such as if someone is going here from there with this type of payload, we want to know about it. That's our highest priority. And down to the last one where if we're just doing a standard SYNAC response, we want to know who's trying to talk to us, but that's not the highest priority. What we want to do is we want to see our web traffic most of all within whatever our session is, a troubleshooting session or a security session. And the way to set that up is you would set up the web trafficking as a higher ID, the top, which would be the first. And then of course, anything like SYNAC or conversational we would set up as our third piece. Let's move on. So what does this look like when we're sending packets across? Well, we have our IP header, standard TCP IP header, or we have our UDP port and our UDP header. And then we have our VXLAN, which is kind of like our layer 2 over the cloud. And that's how we're basically allowed to send that traffic across to our other targets, or to our listening systems, if you will. Because we don't have direct access to layer 2, most of this being software-defined networking, we have to have another way to actually send that traffic across. In that technology, we're using VXNet. And you can also see, as we have a note, any packets that are over 8,946 bytes will be truncated. We can't send too many overtly large packets and mirror them across the entire system. It takes a lot of processing power to do that. And we don't want it to degrade your network, and we don't want it to degrade your experience. Let's move a little further. Now I'm going to turn it over to Eric so that he can show you a demo of how this is actually working in real time. Eric, take it away.
Thank you. Hold on here. Let me change presenter. There we go. So just very quickly, go ahead and show the demo environment I've got. I've got some nodes on the left that are generating some traffic, just generally going out to the internet. I'm going to show you actually what the screens look like for the AWS traffic mirroring, and we're sending everything to a couple of sources. As James mentioned, AWS traffic mirroring, 3 things that you've got to set up. First thing is usually a target. I've got a mix and match here of, at the top, some load balancer targets. At the bottom, just some general network interface targets. Simply doesn't matter where you send it to, either or. What we see in most cloud environments is, as you look at how tooling can be highly available or built with AWS best practices, that's where we see beginning to use load balancers, multiple targets behind that, and being able to use a lot of cloud-centric resources to ensure that your data is available regardless of which instance is in use. Likewise, we use any number of filters that might be there. In this case, I've got a filter set up on another system I've been working on that's only sending SSL or TLS traffic. In what we'll show you here in a minute, we're just sending all the traffic around. And your sessions just end up looking very specifically kind of like this. You get all the details, what your source ENI is, the targets, the filters, everything from the VNI, a lot of details that you can get from this UI. I'll also say everything that you've been seeing, you can also configure via CLI, so any number of API calls that you want to make, and set up any of these in any sort of automated scenario. What I'm going to jump to is just fairly quickly what this ends up looking like inside of your tool. So I'm going to use one of the first tools I talked about, which is Moloch. So Moloch is a packet capture and indexing solution. It's completely open source, and all it's doing is it's bringing in these sessions. I'm going to go ahead and turn any of my filters off and see what we've got. This is a real-time view of all the traffic that's happening from my nodes that are generating traffic. What you're going to notice here, and I just want you to look very briefly at the destination ports. Besides there being a lot of port 22 traffic, which is back to me or wherever else it may be going, you see there's a lot of 443 traffic. And that's one of the things that we've begun to notice at Nubeva as we start looking at what's happening inside of monitoring today. One of the problems we started to see, whether it was here in AWS or even on premises, most all of the traffic that you gather is all encrypted now. So whether it's going to all the traffic to Google, stuff back internally to AWS, all these websites are now encrypted. So the visibility that we used to have is gone. I'm not really sure what's inside of any of this traffic. I just kind of know where it's going. And we've seen that that's brought some real problems back into how we view monitoring and what it allows us to do. So with that, I'm going to go ahead and turn it back over to Steve, who's going to dive a little bit deeper into this problem and show you how we solve it.
All right, thanks, Eric. Hopefully everybody saw that. So fundamentally, right, AWS is, we have tools. AWS has solved the copying of traffic, but we're seeing now an increasing problem where the traffic is all encrypted. And we're going to dig into deeper in that because it's not the same encryption that you used to see, and that's causing even more complications and problems. So the challenge here is if you want to inspect your traffic and most of it's encrypted, what do? We can now get it. We have tools to analyze it, but they can't do much if they can't see into the payload. So the reality here is, as we talked about, your traffic now is encrypted, and as a result, you can't see all of those threats and problems and challenges. It's sort of like trying to look at a redacted document and figure out what the heck is going on. Organizations are forced to infer, which ultimately leads to a number of issues we'll touch on. So the challenge here on top of, I mean, encryption's been around forever, but certainly when you're in the cloud, it's the #1 recommended state of operation for security. However, it's not just your father's encryption. There's a next generation of TLS that's arrived, and it's here. And there's a whole set of protocols and ciphers that are starting to evolve and emerge. The biggest one is this idea of perfect forward secrecy, if you've heard of it. It's also, it's born from Diffie-Hellman algorithms. It is actually instantiated in a new standard that's being widely discussed, TLS 1.3. But to be very clear, TLS 1.2 is being deployed with perfect forward secrecy everywhere today. In fact, it is the default standard for every AWS service and service call and platform call, as it is for every other cloud provider, as well as every internet delivered service. We've also seen PIN certificates causing problems for a period of time of inspection, but we also have new ciphers that are also showing up. What's a Cha-Cha 20, right? I remember AES, but now there's AEAD mode with GCM. So there's a whole new set of innovations and elevations to improve security, and it's coming whether you like it or not. As I pointed out, and in some cases we're starting to hear rattlings that regulatory enforcement might be coming to adopt. Certainly some announcements are happening all over the place. This is coming. Now, why this is significant is that the new standards fundamentally break the traditional technologies for out-of-band decryption. Right? Traditionally, there's two ways to do it: out-of-band decryption and in-band decryption. So out-of-band fundamentally does not decrypt this new style of encryption with perfect forward secrecy. And in-band, the challenge of in-band or man-in-the-middle type solutions is that when you start looking at cloud environments and moving out of a data center into cloud, A, they don't scale to cloud scale. And B, there really is no middle in the cloud. Your ability to go and put, or your desire, or DevOps' support for putting something in the middle, a bump in the wire in every connection and every call to inspect traffic is commensurately low. So where that leaves security operations is fundamentally their traditional tools are taken out of their toolbox. So their ability to detect goes down, their ability to respond goes down, resulting in higher risks and higher costs to get to the same point. And DevOps too has a problem. Their ability to actually diagnose and troubleshoot problems that now they can no longer crack open the packets and see what's really going on the wire goes away, resulting in lower service or higher service response costs. So the reality is let's look at this one level deeper, so that hopefully we can demystify what's going on when I say, hey, fundamentally out-of-band, traditional out-of-band does not work anymore. So in cloud, out-of-band is preferred, right? Sitting on the sidelines, just like the traffic mirror, not affecting cloud performance and application performance. If you look at the way traditional decryption worked, is an out-of-band decryption is you would grab copies of packets from, look on the left, a generic application cluster, clients talking to an application talking to a cadre of private or public cloud resources that are all meshed together, serving each other and serving the app server or the web server. So copying packets over to a decryption system to decrypt. If we peel back what happens inside of these systems traditionally, is to decrypt, you actually need the packets, and you actually need the session secrets, also called the symmetric keys. It's the final secret that was negotiated through the handshake between a client and a server, or a server and a server. Every session has a different key set, and it's exists just purely for that session. So you need those session secrets to decrypt, and along with the packets. And in traditional decryptors, you would load into the decryption system a public-private key pair, and that system would regenerate those session keys from the handshakes and the packets to redetermine the session keys and decrypt when they're not in line. The fundamental answer, without going into, and it would probably, there's tons of information on this on the internet, what's changing with Diffie-Hellman and perfect forward secrecy and TLS 1.3 is this simple. With Diffie-Hellman, session secrets are not generated from the public-private key pair. So as a result, you can't regenerate those keys and those session secrets. And as a result, you can't decrypt. It's really that simple. And this is the fundamental problem that's facing organizations today. All of their existing mechanisms to decrypt out of band have basically gone offline the more perfect forward secrecy is being adopted. This leaves the other alternative that we mentioned, which is man in the middle, which is whether it be a load balancer or a firewall, something that you have in the middle to pull out decrypted packets. There's two issues. One is there's no middle in the cloud, so it's not really effective for all of that back-end traffic or tier 2 level connections. But also we're seeing those systems starting to rattle under the load and the performance scaling requirements of cloud, even on the front side connections and sessions. So the answer is that the ideal answer would be as a solution that actually could do out of band. Since it's cloud, it would be software based. That can support all these modern ciphers and ultimately supports cloud architectures, north, south, and east, west, that works with Kubernetes and containers and the like. And ultimately, that's what a number of companies are trying to tackle this. Nubeva tends to be way out in front on this. We've introduced a solution that does just this. I'll be referencing that. This is not intended to be a sales pitch, but we'll use this as a reference discussion on what's possible today. So Nubeva actually has a solution to do this. And here's the basic concept. As we go back to this picture, the idea is to decrypt, you need the session secrets and the packets. I told you that there's no way that you cannot regenerate those sessions secrets anymore. The fact is that they exist one place and one place only, and that is real time. While the session exists, the keys exist. And the simple idea is, what if in real time you could extract those session secrets and recover those as an asset and forward those to an out-of-band decryptor system? It's a fundamental, simple idea. It is the only way to do this out of band. And ultimately, that is what we've actually, Nubeva has commercialized and put into a scalable, easy system. So it looks like this. On top of a VPC traffic mirror, you can actually then deploy a new kind of decryptor. It's a software-based decryptor. Without the need to regenerate keys, these systems can be much leaner and much faster, allowing them to scale out. Also in cloud, being software-based, it makes sense for it to be a containerized system that allows you to deploy it anywhere. You can deploy it on a tool instance, or you can deploy it on dedicated VMs to create a service or a dedicated VM appliance of sorts. As a container, they're also super scalable in parallel. Now, instead of loading public-private key pairs, which actually has all sorts of operational complexity and security and risk, there's actually the idea of a TLS sensor, a microservice that you can load full-time or on demand as needed onto a workload. And this sensor is capable of discovering and learning all of the session secrets for each session in real time on that host. And it's important to note in this model, it actually can you can actually then see sessions not only out to clients down on the bottom, but also to AWS services. Let's say you're using DynamoDB as a system, as your database. You now can actually see those sessions and the session traffic on that as well, and unlock those packets. And ultimately, as you describe, as the system or this microservice learns the keys and the final session secrets, it actually forwards them back over to the decryptor through an encrypted key plane that is separate from the data plane. And then ultimately, the decryptor matches the key to the packet stream or the PCAP file and decrypts out to the tool. In fact, it actually outputs not only decrypted packets, but it also outputs the original packets so that the tool can read outer original certificate telemetry, for example, but also be able to see a decrypted payload. And in this model, it's rather interesting because the system actually provides full decryption capability, even of the TLS 1.3 handshake, which is encrypted, allowing organizations to actually provide a higher level of moderation and trust and scanning over those handshakes as well. Something that's part of the new standard and pretty unique. So with that, I told you that this is not possible originally, that out of band. This restores out of band capability. Let me turn it back over to Eric to show you now the same demo with decryption added on to the traffic mirroring. So let me find you here, Eric, and flip control with the ball back to you.
Great, thank you. So we're back here. I just wanted to show I got a couple traffic mirroring sessions going, but in this case, I actually do want to show a little bit deeper on the filter. As we talked about earlier, you can configure these filters, set up for whatever type of traffic you want. In this case, all I want is actually 443 traffic. Now, I do want to call attention to one note when you're writing filters, just kind of so everyone, just so you remember, there's an inbound rule and there's also an outbound rule. So all my rules, both inbound and outbound, are basically the same. I'm looking for anything source or dest going to port 443, going anywhere. So that's the filter I'm using for my traffic. So all that SSH or NTP traffic, all that other traffic that we'd seen before, we're only going to look at just TLS SSL traffic right now. So I'm going to go ahead and come back over here to Moloch. We're going to refresh this. And so for me, I'm on out here in Los Angeles, so it's about 10:30, 10:32. And you can see this is the latest traffic I've just got in. So now what I'm going to do is, you'll see here under dest port, before we had a lot of 443s. Now you'll also see there's some port 80s sprinkled in here as well. And I also want to reiterate, I'm only sending port 443 from the source using AWS VPC traffic mirrors and sending that to the destination, which in this case is Moloch. Really, my destination is that load balancer, which is then forwarding it on to my Moloch Open packet capture solution. So we're going to dive a little deeper into something here. So I'm going to scroll to here, and if you see this one packet at the top that I have highlighted, it's going to secure.icar.org, actually, which is in Germany, DE, the country code there. Now, you're probably familiar with ICAR. More on that in a second, but I want to look at this packet. So it's encrypted, 4443. And you'll notice the encryption version is TLS 1.2. So this is encrypted with elliptical curve, Diffie-Hellman ephemeral. And using out-of-band methods, it should not be possible to decrypt this. This is a perfect forward secrecy encrypted packet. And sure enough, as we look at the 443 packet, everything is completely encrypted. We have no idea what this traffic is. But I want to call your attention to this packet right above it. You'll notice it's also to the same destination, to Germany. You'll notice it's port 80 though. It has the exact same high port, 52602, and it also has the exact same timestamps. Let's look a little deeper at this packet. Now, if we look at this port 80 packet, you're going to see what request was actually made, geticar.com, but most importantly, you're going to see the response. I'm sure anyone out there that's worked in security long enough has seen an ICAR test file. The thing we always use is trying to find out, is my IDS working? Is my AV working? This test file will always give you that positive confirmation that your tools are working. And when that's encrypted, the tool's not going to see it. But with Nubeva, we can decrypt that and show you now that port 80 traffic in addition to that 443 traffic we put out at the same time. And by the way, regardless of what the tool is, we can still find it. For instance, here's some traffic going to 2600.com. 2600 is often flagged as a hacking website, for instance. Again, TLS 1.2 encrypted, elliptical curve Diffie-Hellman, yet notice right above it, now on port 80, same high ports, same timestamps. And with this traffic, now we're seeing exactly what was on that website and exactly what was downloaded. You can't hide anything inside of the encrypted command and control traffic or whatever it happens to be. And by the way, just so you know, there's nothing up my sleeve. So for instance, here is BBC traffic, same high port, same everything else. When I look a little bit deeper at this BBC traffic, you can tell that I'm decrypting it. I'll end with one thing here. One of the things that's really tough to do is actually decrypt TLS 1.3. I know that this the traffic I'm showing you going to this specific host, this host is actually a host on Google that we've gotten some traffic from within the past hour. Just to show you here, we will look at this traffic, and you can see very specifically, this is TLS 1.3 using AES 256 GCM encryption. This is a completely encrypted communication to Google. We cannot see inside of it whatsoever. And encrypted with TLS 1.3, for a lot of things out there, even in band, that's problematic. But if you look right above it, port 80, same high port, same timestamp. If we look at this traffic, now the first thing you'll notice is we actually can still see everything we can from the intermediate certs. Anything that's not there is just non-ASCII code. But then scroll down a little bit, and now you start to see things completely unclear. And you can see the entire source code for whatever Google Doodle happens to be available today. So that shows you that we have the ability not only to decrypt standard TLS 1.2 with perfect forward secrecy, but also anything that's using the more advanced TLS 1.3 encryption. And we can show you all those middle steps in the all those steps in the middle. I'm going to close this by showing you what my demo environment really looks like. So the tools on the right were all the same, but actually what was generating my traffic was a Kubernetes cluster. All of the traffic that you saw generating was being generated by a cron job that runs every minute, and it spawns a container that makes approximately 300 TLS connections outbound. And then that TLS container goes away. The Nubeva agent runs as a daemon set, so we run on every node. So regardless of the number of containers that come up, we're able to grab these keys from containers that are lasting no more than a minute, and actually we can grab it from containers that last no more than a few seconds, grab the session keys, and decrypt that traffic on the fly, even if that container is already gone. So with that, that's the end of the demo. We'll pass it back to Steve.
Great, thanks, Eric. Let me figure out how to take the ball back. And there we go. So the interesting thing here is that as we kind of look through this, so you need visibility, you want visibility. There's tools available. You can now get the traffic, and decryption is also viable. Putting the out-of-band option back on the table, if you're very clear about this, the VPC traffic mirroring is an out-of-band solution. The decryption is a companion solution that basically decrypts that traffic so that your tools can do the job and your teams can get the effectiveness and efficiency through the information they need. So a couple of things to just help kind of break this down of how we have joint customers, so in AWS, using this and using these solutions. Let me walk you through a few scenarios to connect the dots. Starting with the most basic, and that is that, you know, just about the number one toolkit for incident responders and DevOps and whether they be the dev or the ops side, tax, et cetera, is to be able to just look at things in Wireshark. Now, all along, this doesn't involve packet mirroring for the time being in this discussion, but very simply, to be able to do a TCP dump, have PCAP files actually out of a critical server, whatever it might be, and actually be able to also get the companion session secrets The decryptors have the ability to read in files as well, and ultimately match the session secrets to it and buffer it, sync it, decrypt it, and pump out a decrypted PCAP file that you can inspect in Wireshark. And this is the most foundational thing. If you call AWS, and James, maybe you can kick in and make some comments here. If you call TAC, the first thing they do is say, have you got a PCAP? And the second issue is if it's all encrypted, they struggle to actually create a support issue. James, any comments on that?
Yeah, that's actually very true. And the thing too is that being able to do this in a remote way is very helpful. And the fact that you actually don't have to go onto your production system, you can mirror your public system. But absolutely, when TAC is called, they need as much visibility into the problem as you can give them so that they can also check on their end. And if you were to hand them over encrypted packets, what are they going to do with that? But if you can decrypt and then say, hey, these are the pertinent pieces of information, even if you don't hand them the exact log per se, but you can actually pull the information out and give them a better idea of what's going on, it's going to help you resolve your cases faster.
Yeah, thanks. Yeah, and it's important to note as we just look at this very quickly, in this picture, the key extractor, the sensor, has 3 different modes. There's a container version, there is a native Linux, and there's also a Windows S channel version. And a single sensor on a host can actually extract and learn all the session secrets from all the sessions going in and out of that host. So some organizations deploy it on only as needed and then remove it and dissolve it when they're done. Some leave it on as part of their standard build and critical clusters, which kind of leads us towards the next level. So this is a very basic manual process. There's also, we have people who are actually then do this, that they'll have a Wireshark instance up and they'll just simply skip the TCP dump and turn on a traffic mirror. And ultimately just flow traffic, capture it, turn it on, turn it off, eliminating that, which also can be automated through TAC and service call automation. So any comments on this one, James, or pretty straightforward?
Yeah, pretty straightforward. This is definitely the way you want to go. Automate, automate, automate.
Yeah, so those two really capture the very first basic thing is that sooner or later somebody should and might need to open up packets. This is how it gets done, simply and easily. Equivalently, of course, that could stream to Moloch, as you saw here, or any other network ECR-based tool for that basic packet analysis, or any other packet analysis tool. But as we move more towards a monitoring use case, in fact, this is one of AWS's 3 top ideas here is monitoring of critical assets. Let's say this is a financial cluster. So you actually pull traffic out of all the key assets in that financial cluster, as well as extract the session secrets, and ultimately can decrypt them over to an intrusion detection system, an APM, network DCR, or other, or all 3. There are many customers who are actually putting these all 3 systems on a scale set behind. Well, we'll get there, but to be able to then have that traffic feeding 3 different systems, even on a single large host. And probably that leads to this use case. And James, maybe you want to talk about this one, where it's not always full time, but it is on some event you move to turn on an elevated level of monitoring.
Yeah, so one of the things that we always try to do is provide an API for any of the services that we provide, and tie them all in together, right? So if there's an event where you see something with your workload, or your customers are experiencing something that's an anomaly that you can grab off of CloudWatch, from there you can set up things that we call lambdas, or short pieces of code, or SMS, or any type of notification systems to go ahead and kick on the traffic mirroring as soon as it happens. Some of those vital seconds between seeing an event and then starting to capture can make the difference between nailing something or resolving something quickly and saving your company time and money, and either in the troubleshooting or even in a commerce sense. So we have a lot of things such as CloudWatch, CloudTrail. We even have GuardDuty, which is another layer of security and analysis on top. So you see an event, it gets triggered, you turn on the traffic mirrors, which is a predefined API calls to go ahead and mirror your production, grab that traffic, and then you can start analyzing it immediately.
Yeah. And in that case, the session secrets are just there when you need them, so that the packets can actually be decrypted. Next use case is actually really a variant of the same thing, which is how do you do this at scale? And the key and beauty of what AWS did is made this so that the packet streams can go directly to a load balancer, and you can put a scale set behind it. And in this case, you actually see a scale set of VMs, let's say running an intrusion detection system with an embedded decryptor and container, and the system can scale up and scale down as you burst traffic up and down at it. Any comments on this one, James?
Sure. One of the use cases I want the audience to think about is, let's say you have a month-end MRP roll for an internal financial system, or you have something where you have a sale or promotions event on something on the internet where you know that your traffic is going to spike. The last thing you want to do is to have your traffic mirroring set up, but not be able to keep up with the auto scaling or the elasticity of your actual workspace or your actual workload. So if your workload can expand, accepting more traffic, but your traffic mirroring is only set up to be able to monitor a small subset of that, it won't be very useful for you. So what you need to do is you need to mirror that elasticity. And that's why we allow it to go to an NLB, because behind an NLB, you can set up your target groups and your auto scaling to keep up with that traffic.
Yep. Now, I realize I didn't explain there's a node here, which is this little cycle thing where the Nubeva key extractor on the left is actually sending things to an interim node. That's actually a critical element. There's a buffer system built off of a cloud database that you set up in your own environment. It's with a short time to live. Let's say 1 minute time to live, but it functions as this incredible scaling function, which allows thousands and thousands of key extractors to function in parallel. And instead of overloading them all to and guessing what decryptor to send the keys to, it actually holds them in a short interim buffer that then gets regularly purged. And ultimately that allows multiple decryptors to pull the same session. Let's say you have multiple different tools that actually are receiving the same stream and all need to decrypt. You could decrypt to once and send to all, or you could actually stay encrypted end to end and encrypt actually on the tool itself. This system actually allows for virtually infinite scaling, both at the decryptor side as well as the key extraction side through that buffer system in the middle there. We could keep going on, but let me just fill in a couple gaps because I know we're coming to the end and we want to get some Q&A and such. A couple things, just kind of summarizing this, putting these two pieces together, it basically has said, puts visibility and decrypted monitoring back as a possibility again. There's broad-based support. The solutions discussed here today support any kind of traffic that you can pin to an ENI, whether it be VMs, containers, or other services. And that'll be broadening over time as AWS matures the service and into the future. It also, as James mentioned early on, all of this, including the decryption side, is tool agnostic. It's all designed to be a foundational capability that allows you to use any tool or tool sets that you need. Tools, security tools, analytics tools. This is tool agnostic. The second part is all of this is very cloud native. It's all modular, it's flexible, it's scalable, and also, as James just mentioned, everything is REST API driven, so you can orchestrate this from other systems, which is the foundation of the cloud. And I think that the last piece here is there's some pretty disruptive economics. VPC traffic mirrors started at $0.0125 an hour. And the decrypt from Nubeva, there's entry points as low as $50 a month. So there's really no excuses from a financial perspective. And if you kind of think about these, typical of cloud, this is 1/10 to 1/100th of traditional data center costing to achieve equivalent, with also entry points that allow it to be made available to an individual analyst or developer or what have you. So pretty interesting, pretty disruptive from that perspective. So that's the net, is that, if you want to get decrypted visibility in AWS, there's now a way to do it. You can get full packet inspection through VPC traffic mirroring and Nubeva TLS decryption, allowing your SecOps to see more, detect more, respond faster, and your DevOps teams to be able to resolve and debug problems faster. So with that, the quick summary of going through. So why don't we, let me look over here. I've been focused on the slides. Let me look over at some questions that have been going through here. Let's see, the first one, actually, let me start sorting through. Let me start with some basics here, and then I'll get to some others. Let's see. James, when did VPC traffic mirrors come out?
Traffic mirroring came out, I want to say at the end of June this year, June 25th, I believe.
Yeah, that was at Reinforce, right?
Right.
In Boston. Yeah. Yeah. Now, are there another lead on tie-in question to that? Are there any limitations or restrictions around mirrors?
Yeah, there's a couple. The first thing is you need to use Nitro-based systems or systems that are identified when you pick out that have a Nitro card. Another thing that I want to make sure that people are aware of is that the traffic mirroring takes along the same routing path as our VPC. So you need to make sure that whatever you're mirroring from your source and your target need to be able to actually communicate with one another so that they can see. Lastly, there's a certain size within the MTU and the packet size. You want to make sure that your packets aren't greater than, say, that limit I pointed out before of 8,996 bytes. Otherwise, we will truncate those packets, and it might make your results a little bit more variable than you were expecting.
Yeah, well, certainly if you truncate some of the data, the payload's useless. Certainly in decryption with yeah. So okay, let's see. So here's one for the Nubeva side, for the decrypt side. Okay, how do you scale up, or how does it scale up? I think I touched on that. The system actually doesn't have a single point of failure except for that buffer system, which is actually a cloud service that you set up inside your own subscription. With AWS, it would be using DynamoDB, which is a fully redundant, resilient, encrypted, infinitely scalable, very low cost database platform. And so the way that works is you can deploy 1 or 1 million key extractors, and they all get forwarded there and held for a brief moment. You can actually set the time to live on the keys. So some people who have the default is 24 hours. Some people ratchet it down to 1 minute. Other people have retention requirements, so they can actually archive off those keys for 30 days, for example, if they're having to do a rolling PCAP store or VCR function for regulatory or compliance. On the decryptor side, those two also operate independently, so there's really no individual choke point on any of that. So kind of cloud style, it's actually a number of modular independent software modules that function and scale up and down elastically with the cloud and with your workloads. So hopefully that answers that. Let's see. Okay, so another one on, well, I've got the mic and talking on my side. What about the secrets? These keys you're talking about, isn't that a security risk? So this is actually, and there's a related question I'll get to here in just a second. So this is very important. These are not the public-private key pairs, which are, if you think of, are the keys of the kingdom. It used to be that public-private key pair, if you actually ever had your private key compromised, every session going in and out of that host was actually could be compromised. So people could record traffic for 5 years and sooner or later get their hands on that key and actually see the traffic. This is different. These final secrets are individual and unique per session. They're basically in the perfect forward secrecy language, they're called ephemeral, meaning they're actually held in memory and thrown away and never written down. All the system is doing is extending the ephemerality. But it's interesting to note that only one session secret, or what's also called a symmetric key or final secret, ultimately is only applicable to one session. So even if one was compromised, at worst case, what's at risk is a single session during the time of that session. When a session is renegotiated or reconnected, depending on your settings, the default is it'll actually renegotiate a new set of session keys. So the risk profile of this model is dramatically different. Related to that is that there's a question which is, well, hackers misuse this technology. And the interesting thing is that it's no different than any other microservice or service you put on a workload. So let's look at each component. So the sensors themselves that extract the keys are actually a microservice and a read-only function. They have no inbound connectivity code inside them. All they do is discover a session secret and forward it. If you don't have the packets, if you don't have the rest of the system in place, they're useless. The second part, though, is that if any system is owned, this is probably the hardest way for a person to try to compromise your system. There are also checks and balances. There's certificates that the keys can only be sent to your database that you set up, et cetera, across those connections and to the buffer system, your decryptors. Similarly, on the decryption side, everything is locked in and keyed in around your subscription. So the answer is actually the reverse. Is actually more secure than the traditional data center model, and actually doesn't require as much kid gloves as required as usual. Okay, here's one. Let me go back to you, James. What does mirroring do to performance of my systems? And what is the impact on host, et cetera? I know you know that question, so I'll just spare reading it.
That's a good question, and we've been asked that a lot. So one thing I need the audience to understand is that when you mirror a packet, you say if you're mirroring 1 gig, you actually will create 3 gigs of traffic. And I know that sounds scary, but hear me out. So the 1 gig of traffic that you're going to mirror, you have the bidirectional piece of sending that traffic to your monitoring system and then back. The one thing that we do is we make sure that it does not impact the production NIC that you're mirroring. If there would be, or it comes to the point where there will be any impact, what we do is we degrade the mirroring process, not the process of your NIC on your production instance to be able to speak. So we, in a sense, prioritize production packets and production traffic first, then allow mirroring second. So that does lend you to have to kind of be thoughtful and prescriptive on how you set up your mirrors to make sure that you're not going to over mirror your system, set up more than 1 mirror, more mirrors than what your system can currently handle. And that comes down to choosing the right instance sizes. It comes down to choosing the right NIC sizes. Remember, the speed of your NIC is determined by the size of your instance. If you're going to have an instance and you know you're going to heavily mirror that instance, you need to account for that when you create the instance and create your public or your production system. Back to you, Steve.
Yeah, great, thanks. Yeah, so and I'll just hit the decryption side. The microservice, the key extractor, is a little less than a 10 meg footprint, and it uses well less than 1% of a single CPU core. It also has a stand down prioritization that if it were to ever spike above that threshold, it actually stands down, so that it's also a contained process. So again, the whole intent here is a minimal impact on production workloads, key to the out of band as well. So let's see, I apologize. We are at the end of the hour. I think there's a bunch more questions. So I think what we'll try to do is we'll try to gather these things and maybe post them in an FAQ, a joint FAQ or blog around this when we post the video on this. I think, so I apologize, we can't get to all of you because I know that we've got the drawing that I want to make sure that Charlene gets to. Before we do that, how to get started. So VPC traffic mirroring is available as GA today. So just have at it. Go in, turn it on. It works. The TLS Decrypt is actually also GA. It's fully available and functional. There's free trials available. Lots of information on both websites, etc. Certainly cloud architects to talk to help you solve your problems. So if any of this was interesting and can help you, we encourage you to dig in and engage either AWS or Nubeva to help you solve your problems. So with that, thank you for being here. Let me turn it back over to Charlene.
Okay, great. Thanks so much. I appreciate it, Steve. Let's go ahead and do that AWS, the drawing for the 3 $50 Amazon gift cards, and then we'll let everybody go. Our first winner today is Deborah Cascardo. Congratulations, Deborah. Our second winner is Victor Grado, and I apologize if I mispronounced your name, but congratulations, Victor. And our final winner today is Sujit Narayanan. So congratulations, Sujit. We'll be in touch with all three of you to get the cards over to you. Just a real quick reminder that today's event has been recorded also. So if you missed any or all of the webinar, you will have the ability to listen to it later on. We are going to be sending out an email post-event that contains a link to access the webinar on demand. And the webinar is also going to be living on the Security Boulevard website, so you can always go check it out there. Just go to securityboulevard.com/webinars, look in the on-demand section, and it should be right there waiting for you. Gentlemen, thank you so much for a great presentation today. Lots and lots of good stuff, and judging by the number of audience questions that we got, I know the audience got a lot out of it. So thanks so much for your time and your expertise. And I also want to thank the audience for joining me today. This is Charlene O'Hanlon, and I'm signing off. Have a great day, everybody.